stop for a moment. Just freeze. Look at your hand. Now place it on the table or the desk in front of you. Press down. It feels solid, doesn't it? It feels real. You trust your eyes to tell you where you are. You trust your sense of touch to tell you what is real. You live in a world of cause and effect, a world where time ticks forward second by second, and where objects stay exactly where you put them until you move them. It is a comfortable, reliable, clockwork reality. But I am here to tell you that everything you are experiencing right now is a lie. The solidity of that table is an illusion. The flow of time you feel is a trick of the mind, and the space between you and the screen you are watching, it isn't empty at all. Over the last 100 years, a small group of physicists have been quietly pulling at a loose thread in the fabric of our reality. And when they finally pulled hard enough, the entire tapestry unraveled. They discovered that the universe is not a machine. It is a ghost story. They found that the floor beneath your feet is mostly empty space, that particles can be in two places at once, and that reality itself might not even exist until you decide to look at it. Today we are going to walk through 10 specific doors. These are the 10 experiments that broke physics. These are the moments where we asked nature a simple question, and nature gave us an answer so impossible, so terrifying, and so beautiful that it forced us to rewrite the rules of existence. Welcome to the real world. Let's begin with the experiment that started the fire. The grandmother of all quantum nightmares, the Double Slit Experiment. To understand why this broke the world, you have to imagine a simple scenario. Imagine you are standing in front of a wall that has two vertical windows cut into it. You are holding a bucket of tennis balls. If you start throwing those balls at the wall, some will bounce off, but some will pass through the windows. If you look at the wall behind those windows, you would expect to see two piles of tennis balls. One pile behind the left window, one pile behind the right. This is how our world works. Solid objects travel in straight lines. But when physicists tried this with electrons, the tiny building blocks of matter, something haunting happened. They fired electrons at a barrier with two slits, but on the back wall they didn't get two piles. They got a pattern of many vertical stripes spread out across the entire wall. In physics, we call this an interference pattern. It is exactly what happens when you drop two stones into a pond and the ripples crash into each other. This result implies something that defies all logic. It means that the single electron didn't choose a window. It didn't go left and it didn't go right. Somehow, that single piece of matter became a wave of potential. It went through the left slit, the right slit, neither slit, and both slits, all at the same time. It interfered with itself. But the story gets stranger. The scientists were baffled. They thought, okay, let's trick it. Let's put a sensor next to the slits to see which path the electron actually takes. They turned on the eye of the detector. They fired the gun again. And the moment they looked, the very instant the universe knew it was being watched, the behavior changed. The wave pattern vanished. On the back wall, two simple piles of electrons appeared. Think about the weight of that. The moment we observed it, the electron stopped acting like a ghost and started acting like a solid particle. It suggests that reality does not exist in a definite state until it is measured. We are not just an audience sitting in the dark watching the universe perform. We are the directors. Our gaze forces the ghostly quantum world to harden into the reality we see. If that makes you feel uneasy, you are in good company. But we are just getting started. If the double slit showed us that matter is a wave, the next experiment showed us that nature is pixelated. This is the Stern-Gerlach experiment. In the 1920s, we wanted to understand the magnetic properties of atoms, something called spin. Imagine an atom is like a tiny spinning top. If you throw a bunch of spinning tops through a magnetic wind, you would expect them to wobble. Some would tilt up a little, some down a little, some would stay flat. You would expect a messy smear of results on the detector covering every possible angle. But when they shot silver atoms through a magnetic field, they didn't get a smear. They got two crisp, distinct spots, top and bottom, nothing in between. This was the birth of quantization. It proved that nature doesn't do fractions. It's like walking into a coffee shop and asking for a drink at a specific temperature, and the barista tells you that you can have a cup of boiling lava or a block of absolute ice, but absolutely nothing warm. And there is no middle ground. This binary reality, this up or down, this +1 or -1, is the fundamental code of the cosmos. It is the reason we have chemistry. It is the reason atoms have structure. And today, it is the principle that allows MRI machines to peer inside your body and save lives. So, matter is weird. But for a long time, we thought at least light was simple. We thought light was a wave, a continuous stream of energy like water flowing from a hose. Then came the photoelectric effect, and Einstein proved us all wrong. Here is the mystery. If you shine a light on a piece of metal, you can knock electrons off the surface. If light were a wave, like water filling a bucket, then even a dim red light should eventually knock an electron loose if you waited long enough for the energy to build up. But that's not what happens. You can shine a red light on metal for 1,000 years and nothing will move. But turn on a dim, weak violet light, snap. The electron flies off instantly. Einstein realized that light isn't a smooth wave, it is a hail of gunfire. We call these bullets photons. The red bullets were too soft to knock the electron loose no matter how many you fired. But the violet bullets? They packed a punch. One shot, one kill. This proved that energy is quantized. It comes in packets. Without this realization, you wouldn't have digital cameras, you wouldn't have solar panels, and our modern digital world would simply not exist. Now let's leave the world of the single particle and look at the connections between them. We have to talk about the experiment that Albert Einstein hated the most. He called it spooky action at a distance. We call it quantum entanglement. This is the concept that breaks our understanding of space. We can take two particles that are created in the same event. They are entangled, meaning they share a mathematical destiny. They are, effectively, the same object. Now imagine we separate them. We keep one here on Earth, and we send the other one to the Andromeda Galaxy, 2.5 million light-years away. Because of quantum mechanics, we don't know the state of these particles. They are spinning both up and down at the same time, living in a fog of probability. But the moment, the exact nanosecond, we measure the particle here on Earth and find it is spinning up. Its partner in the Andromeda Galaxy will instantly snap into the down position. There is no time delay. It happens faster than the speed of light. How does the second particle know what happened to the first one? Did they send a signal? No, that would take millions of years. The connection is immediate. This experiment, proven in the 1980s by Alain Aspect, killed the idea of locality. It suggests that space, the distance between things, is just an illusion. On a fundamental level, everything that has ever touched is still connected by invisible threads. The universe is a single, breathing web. But if space is an illusion, what about emptiness? What about the vacuum? This brings us to the Casimir effect. If you take a box and suck all the air out, take all the atoms out, shield it from all radiation, what is left? You would say, nothing. You would be wrong. Physicists discovered that empty space is actually a boiling ocean of energy. Virtual particles are popping into existence and annihilating each other in fractions of a second, everywhere, all the time. To prove this, they placed two tiny metal plates extremely close together in a vacuum. Because the plates were so close, the quantum waves between them were restricted, but the waves outside them were crashing against the plates with full force. The result? The plates were pushed together. The pressure of nothingness crushed them. We can actually weigh the void. The emptiness has muscle. It tells us that there is no such thing as a true vacuum. We are swimming in an ocean of infinite energy that we are only just beginning to understand. And just when you think you understand the rules of influence, along comes the Aharonov-Bohm effect to break them again. In classical physics, to move a ball, You have to touch it. To move an electron, you need an electric or magnetic field to touch it. But in this experiment, scientists shielded a magnetic field completely. They hid it inside a coil so that no magnetism could leak out. They fired an electron past the coil. The electron never touched the field. It was like walking past a house with the windows closed and the blinds drawn. And yet, the electron changed. Its interference pattern shifted. It knew the field was there. This suggests that the electron felt the mathematical potential of the field without ever touching the force itself. It's like getting a sunburn from a sun that hasn't risen yet. It shows us that the mathematical abstractions, the invisible potentials underlying our reality, are more real than the forces we can measure. Usually, this quantum weirdness stays hidden in the microscopic world of atoms. We don't see cars being in two places at once, but if you make things cold enough, really cold, the ghosts start to show themselves in our macroscopic world. This is the miracle of superconductivity. Friction is the tax we pay for movement. Everything that moves loses energy to heat. It's why your car engine gets hot. It's why your laptop needs a fan. But at temperatures near absolute zero, the electrons in certain materials stop fighting each other. They pair up. We call them Cooper pairs, and they move like a synchronized army. Resistance drops to exactly zero. You could start a current flowing in a loop of superconducting wire today, and without a battery, it would still be flowing 1 billion years from now. It is perpetual motion right here on a table. And then there is superfluidity. This is perhaps the most disturbing thing you will ever see a liquid do. When liquid helium gets cold enough, it loses all viscosity. It has zero friction. It turns into a Bose-Einstein condensate. Essentially, all the atoms in that cup lose their identity and become one single giant quantum object. If you leave it in a cup, it won't stay there. It will creep up the walls of the glass, defy gravity, flow over the rim, and drip down. It will flow through cracks so small that air molecules can't pass through. It creates a fountain that never stops flowing. It is matter behaving with a mind of its own, a glimpse of how the universe acts when the chaos of heat is removed. So, we have looked at the tiny, and we have looked at the cold. But what about the massive? What about the planet beneath our feet? Let's step back from the quantum edge and look at the Foucault pendulum. You have likely seen these in museums, a heavy brass ball swinging back and forth on a long cable, slowly knocking over pins in a circle. You stand there and watch the ball rotating, hour by hour. But your eyes are lying to you again. The pendulum isn't rotating. The pendulum is the only thing in the building that is staying still. It is the museum, and the foundation, and the city, and you, and me, that is twisting beneath it. The pendulum swings in a fixed plane, locked to the universe, while the Earth spins under its feet. Before this experiment, we knew the Earth spun because of calculations. But this was the first time we could feel it. It makes you realize you are standing on a giant spinning carousel, hurtling through the dark. Finally, we must talk about time itself. We tend to think of time as a constant, a river that flows at the same speed for everyone. But the muon lifetime experiment proved that time is personal. A muon is a heavy, unstable cousin of the electron. They are born when cosmic rays hit the top of our atmosphere. Here is the problem: muons die young. They disintegrate in 2.2 microseconds. Even traveling at the speed of light, they should only make it about 600 meters before they vanish. They should never reach the ground. But if you set up a detector at sea level, it will scream with activity. Millions of muons are hitting us right now. They are passing through your body as you listen to this. How? How did they survive a journey that should have taken lifetimes? Einstein had the answer. Special relativity. That because the muon is traveling at nearly the speed of light, time changes for it. To us, standing on the ground, the muon's internal clock slows down. We see it living longer. But for the muon, the journey was instant. From the muon's perspective, space itself collapsed. The distance from the top of the atmosphere to the ground shrank from miles down to a few meters. This isn't just theory. This is the proof that time is not a universal constant. Time is a geography, and speed is the vehicle that drives across it. Your future, my past, and the muon's present are all relative, depending on how fast we are moving through the cosmos. So, where does that leave us? We started this journey by looking at a table and calling it solid. We end it by realizing that solidity is a myth. The double slit taught us that observation creates reality. Entanglement taught us that everything is connected. The Casimir effect showed us that emptiness is full, and the muon showed us that time is flexible. We used to think physics was about discovering the rules of the game. We thought if we looked hard enough we'd find the gears and the levers that run the universe, but these experiments didn't show us the gears. They showed us the magic. They revealed a universe that is far more fluid, far more mysterious, and far more intimate than we ever dared to imagine. We are not just observers on a rock floating in space. We are participants in a quantum mystery that is still being written. The universe is not a place of hard answers. It is a place of infinite possibilities. And perhaps the most mind-bending experiment of all is the one happening right now, the fact that atoms, forged in the hearts of dying stars, have come together to form a brain that can wonder about its own existence. The game has only just begun.